Hi everyone, my name is Taha. In this video, I will be showing you a military-style unmanned aerial vehicle simulation developed using Unity and a custom WPF interface connected through a custom TCP communication layer, specifically designed to resemble a defense system prototype. You will see how to real-time control, radar feedback, and a system communication come together in a compact simulation. This simulation was made to test remote control, targeting systems, and integration with external interface. Let's dive in. This project is designed as a prototype for real-time control and simulation of unmanned aerial vehicles. Built in Unity, and it's designed to receive real-time commands from a WPF-based interface via TCP and IP. The unmanned aerial vehicle is not controlled directly inside in Unity. Instead, all actions are simulated based on external commands sent via a WPF interface. The goal was to simulate an unmanned aerial vehicle that can respond to external commands such as target lock, directional movement, and firing actions. The user interface is designed with a tactical military-style layout in WPF. Flight and fire commands are sent via TCP client and handled using network stream and multi-thread message parsing for responsiveness. These commands are transmitted over a TCP socket to Unity, and the aircraft reacts accordingly. We can switch between aim mode and flight mode, fire the weapon, and send directional commands. Unity handles the real-time 3D simulation. The drone model can be controlled via incoming TCP commands that are parsed and executed within the simulation. On the UI side, a WPF application allows the operator to send specific instructions, like moving the drone, aiming, or simulating a firing sequence. Additionally, Unity's render output is streamed back to the WPF interface, creating a two-way communication loop. In Unity, the drone doesn't have internal control. Instead, it listens to commands from the WPF side driven by network messages. The aircraft reacts to external commands rather than internal controls. Each command updates its state machine, meaning the Unity's simulation is purely reactive, like a real-world drone receiving commands from an operator. All incoming messages are encoded into a queue, which is processed in the main thread to ensure thread safety and consistency within the Unity update loop. Each event is logged and sent back over TCP, giving the WPF operator real-time status updates. One of the core features is the real-time video feed. Unity's game view is streamed to WPF as a live feed using a texture-to-byte array conversion method. Unity renders the scene to a texture, converts it to a PNG byte array, and streams it through TCP to the WPF site. Unity renders the camera view into render texture, converts it into a PNG byte array via texture2d.encode to PNG, and streams it to the WPF interface over TCP. I downscale and compress each frame before sending it over to network, which allows for near real-time display on the WPF interface. This approach keeps frame size minimal and transmission efficient, even over slower connections. There is also a radar system that tracks all simulated entities in Unity. Radar tracking is handled by mapping Unity world coordinates into a 2D coordinate system. Each object's position is converted into radar coordinates, and the WPF site uses this data to render a real-time radar overlay. This gives the operator a quick view of what's happening without relying on the video feed. The communication layer is designed to be lightweight and responsive. Logs are streamed with timestamps, and all operations are handled asynchronously to prevent frame drops or input lag. This was a great experiment in combining Unity simulation with external control and visualization via WPF. If you are interested in simulations, drone tech, or system integration with Unity, feel free to connect with me on LinkedIn or check out my other projects and subscribe to follow along. Thanks for watching.